Okay, so now we're back. This is we're back, and we just looked at vectors, and we know that we can divide up motion into x's and y's. And what's one of the nice things about dividing things up into x's and y's is I can add a whole bunch of, let me turn this off. So I can add a whole bunch of crazy vectors to each other, and I can ask, well, what's the result if each of these vectors is a force that's acting on something, and I want to add them all up? What's the final thing that adds up here? And what's great about this is if I divide them up into x's and y's, all I have to do is add up the x's and add up the y's, and they become my new sides of a triangle. And the sum is the result of all of those x's and y's being used to it's the result of all those. So the result of these added together will be this, and this is the x's, this is the y's added together, and this is the x's added together. And so we can use our Pythagorean theorem again. So this is what we're going to do to figure out that momentum is conserved. Now, to do this part, I need to make sure that the reflecting border is off. The reflecting border adds a complexity to this, and it makes it hard to see that momentum is conserved. And if you're an experimental physicist and you're designing an experimental apparatus to look at the momentum of particles at your particle accelerator, you would have to think very carefully about the particle interactions with the border. So we're not going to use the border in this because it makes things go much more complex. But let's look at that. So let me get my calculator up here, and let's add up at our beginning. So we're all the way back at restart. And let's add up all the momentum in x. So this is p sub x. That means momentum in the x direction. The x part of all of these arrows, we're going to add them up. So it's 0.465 minus 0.750 plus 0.5 minus 0.210 equals. So I just added up everything right here, and I got 0.005. So in our x direction, our total momentum before the collision is 0.005. Now let's find out what it is in the y direction. So that would be minus 0.013 minus 0.750 plus 0.250 plus 0.430. So in the y direction, it's 0.083, minus 0.083. Minus is very important with momentum. Okay, so let's have them collide. And I think 3 misses. Yeah, 3 misses. The other one does. Okay, let's press stop. Okay, now things have changed. The arrows are going different ways. They're different sizes. Let's add it up and see if momentum in our collision was conserved. So it'd be minus 0.612 plus 0.036 plus 0.5 plus 0.081. And we got our original result. Our original in x was 0.005. It's divided up very differently amongst the particles, but our momentum in x is conserved. Let's check our momentum in y. So that's minus 0.353 plus 0.505 plus 0.250 minus 0.485. Voila! It is also conserved, negative 0.083. Great. Okay, so that is conservation of momentum. Let's go back to our article. Okay, so we show the conservation of momentum. Da, da, da. And I talked about no reflecting walls. And this is the second, I think this is the second suggested break. do take some time to play around with these simulators and have fun and verify for yourself. You know, at least the simulators may be correct or may not be correct, but I think within the parameters I've given you, the simulators will work really correctly for you. So take some vectors are only going to show up maybe once or twice more in this class, but if you're doing physics, vectors are going to show up a lot. So maybe take some time and play around with the vector simulation. Take some time and play around with the pendulum and do your own experiments with it. See if pulling it back higher, making it longer, making it heavier, which ones make a difference. Galileo was fascinated by that and spent a great deal of time with it. So it's very fun to do that too. Okay, so now we get to the actual homework where we put it all together. And you'll need either a Newton's Cradle that you have at home already. You can use the online simulation of the Newton's Cradle, which we have up here. Or I have a little video that shows you just need a ruler. These old style rulers have, I don't know how well this will go in video. They have a groove that goes down the middle, and you can put marbles. You need a set of marbles that are going to be the same size to do this. And you'll notice that it works the same as a Newton's Cradle. Okay, so that's one way you can do that. Okay, what to do? Now this is the part where you might want to go and break out the packet and read through this part a bit. Okay, because this is about pulling all these words together and making them your own. They belong to you now. So step one, it's going to use fancy words, right? Do work. We now know there's a definition to what work is. By adding potential energy, there was a definition for what potential energy was, to the thermodynamic system we are observing. The amount of energy you should add is enough to, lift one bob to any height you pick. So we break it down. The thermodynamic system we are observing is the Newton's Cradle. So it sounds fancy, but that's the Newton's Cradle. So I'll just open that up. So we're going to do work by adding potential energy to the thermodynamic system. That step one is just that. That's all that is. And the key to this homework is realizing that those words are what describe what you just did. Okay? The next part, potential energy is M times g. You pull the ball back a little or a lot. That's it. The next part is let the ball go and observe the complete transformation of potential energy to kinetic energy in accordance with the first law of thermodynamics. Again, fancy words. What does that mean? All that means is you started out with some potential energy back here. When you let it go, as we saw with our pendulum example, all of the potential energy is converted to kinetic energy. The ball doesn't stop here because it has a velocity, it has kinetic energy. It stops here when something comes when it impacts something. When it impacts, it transfers that energy to this guy. So to observe all of the potential energy being transformed to kinetic energy, all that means is I watch it go from here to here. That is what that step means. Okay. Observe the conservation of momentum during an elastic collision. Again, really big words, but look at this. So what that means is when I pull it back, and when it comes down here, it has a certain velocity and it has a certain mass. That m times v when it hits is going to equal the m times v at the end. That's all that number 3 means. So all you do is observe that when this ball hits, a ball comes off the end with equal speed. There you go. You have observed the conservation of momentum during an elastic collision. The next experiment is to do the same. These are actually just repeated from the one above, but you're going to do it with 2 balls. So all you do is you pull back 2 balls, or if you're using the ruler, you thwack 2 marbles towards something, and you observe that 2 balls come off the end. Okay, that's all that. Now, observe conservation of momentum would be just as happy with 1 ball leaving Newton's Cradle going twice as fast. That would be perfectly fine, because how you figure out momentum is 2 times the mass of one bob to the mass of the other bob going into it. They both have the same speed when they hit, so this is the momentum going in, and that is perfectly equal to twice the velocity times the mass of one bob. But that's not what happens. It never happens. I should probably make this like bold and like in blue. That never happens. Okay? There's also a little times there I need to get rid of. Okay. The reason is because the energy is conserved is the energy this as before and after. So the reason why is you have to look at this math equation. So this is the one part where you need to go and look at this particular math equation. If you had one bob going twice as fast at the end of this collision, energy would not be conserved. So that's why one ball going twice as fast never comes off the end. If you're doing the marble experiment, let me just stop this guy from clicking. If you're doing the marble experiment, there's a further experiment that you can do where when you flick marbles down, use a bigger marble and flick it down towards your regularly, to 3 or 4 of your regularly sized ones and observe what happens at the end. Okay, what you need to hand in is a sentence or two. Get a student to write it. So you don't even have to write this. Get a student to write a sentence or two verifying that you have taught them the following. That the reason the same number of balls always comes off the end of a Newton's cradle collision as the number of balls that went into it is that both momentum and energy are conserved in a collision. This disproves the idea that momentum and energy are the same thing. Momentum would be conserved if one ball came out of the collision twice as fast as 2 balls that went into the collision, and this does not occur. All right, that is it for the homework. There's a little thing at the end going deeper about positional energy, and the key to this positional energy is the potential energy that we put in was positional potential energy. And positional energy has a very interesting implication when it comes to the Bohr atom. The mass of a hydrogen plus the mass of an electron, mass of a free electron plus the mass of a free proton, is greater than the mass of a hydrogen atom. And that is weird since a hydrogen atom is just an electron plus a proton. But we will find out in coming weeks that just as we know that motion is relative when we're going a constant velocity, and time we haven't introduced yet, but time is going to be relative. And then we're going to find that even our mass is relative to our point of view and to our perspective. And E equals mc squared is one of the ways that we adjust for the difference in positional energy. Okay, that's it. You're done. If you just show that to a student and get the student to say they learned those 2 things from you, that is it. You're done with this homework, this massive 23-page packet. All right, bye.